Swayam Prabha. Digital India. Educated India.
Hello students, welcome to this lecture. In the last lecture, we are discussing about vibrational spectroscopy, and in particular we are discussing about the vibrational spectroscopy in diatomic molecules. We carried out our discussion within harmonic approximation. So, therefore, we obtained the selection rules of delta V equals plus minus 1, and in today's lecture we will continue our discussion from there, and we see how real life vibrational spectra are different from the spectra that one obtains from harmonic approximation. This is what we are going to discuss in today's lecture. So, we go beyond harmonic approximations. The two important approximations that we had in our previous discussion are given here. The first one is that we defined our potential to be harmonic potential V equals half k x square. This suggested that the molecule is elastic. That means, I can keep on stretching or shrinking the molecule, or I can keep on giving more and more energy to the molecule, and molecule will simply vibrate more and more. That means, the bond distance is bond is extremely elastic, it will never dissociate. But we know that in reality that is not the case. So, therefore, defining the molecular potential as half k x square, which is a harmonic potential, is a limitation by itself. And the second assumption or limitation that we have in our previous discussion is that we took this dipole moment, electric dipole moment, and we did a Taylor series expansion. But with this Taylor series expansion, so this is the 0th order term, this is the first order term, second order term, and so on. So, we often truncate after first order, we ignore the second order and higher order terms, and that also provides another approximation. So, both of them are called harmonic approximation. Here the harmonic approximation is made into the potential. Here the harmonic approximation is made onto the electric dipole moment that we are discussing. So, therefore, when we invoke the electric dipole moment to be harmonic, that means we truncate only after the first order, we call that electrically harmonic, and when we use a potential which is harmonic, we call that mechanically harmonic, because the mechanical model itself is harmonic. Now, what we do now is that we go beyond these two harmonic approximations. The first one we will consider as electrical unharmonicity. This unharmonicity term takes us beyond harmonic approximation. So, therefore, when I am talking about electrical unharmonicity, of course, you would immediately recognize that I am going to talk about the truncation of this dipole moment operator. So, if you recall our discussion from the last class, we defined the transition dipole moment integral as something like psi v prime mu psi v double prime, which was given by, since mu e is a constant. So, therefore, the first term becomes 0. We discussed that in the this has half over here. So, this is the curvature of mu with respect to x, this is the slope of mu with respect to x, and these two integrals in the last class we discussed that this integral will survive when delta v equals plus or minus 1, this integral will survive when delta v equals plus or minus 2. So, even when we are considering harmonic oscillator potential, if we expand our mu beyond first order, if we expand our electric dipole moment beyond first order, that means taking second order, we can still see unharmonicity in the spectra. By what do I mean? If the spectrum is completely harmonic, that means I will see only one band, that is from 0 to 1, and this band will appear at h bar omega, that was called fundamental band in the last class. If we see 0 to 2 transition in a molecular spectrum, then we know that delta V equals plus 2 has become allowed. So, one way to explain that could be that this quantity, the second order coefficient, is not that small to be ignored. So, therefore, we must consider. If we consider this and obtain description for 0 to 2 transition, we are calling that as electrical anharmonicity. So, when we express our dipole moment beyond first order or beyond harmonic approximation, so that gives rise to electrical anharmonicity. Now, but electrical anharmonicity can come when we have, even when we have harmonic oscillator as the potential. But we know this harmonic oscillator potential has a problem. The bonds that we see, the molecules are not elastic. It is not like that I keep on giving energy to the molecule and the molecule will keep on vibrating, retaining its molecular architecture. What would indeed happen, the molecule absorbs more energy and finds a dissociation pathway to become if it is a diatomic, then it becomes 2 atoms, or if it is a polyatomic molecule, it makes many fragments. So, molecule absorbs this energy along a particular vibrational mode and then molecule breaks down. So, this can be described by the so called mechanical anharmonicity, where we do not use this V equals half k x square assumption, rather we have some V equals V anharmonic model. So, that means this is not V equals half k x square. So, in this case what happens, R equals the first term and then I write the second term. I just wrote down this transition dipole moment again, but now you remember that this potential energy is not harmonic oscillator, rather it is V anharmonic. Some other we will discuss in a moment time what can be a suitable anharmonic potential, but suppose we have an anharmonic potential which is different from harmonic oscillator problem. So, in this case, even when I do not consider the higher order term, let us consider only the first order term, we see that in case of harmonic oscillator this term became 0 when delta V was not equal to plus minus 1, but that was a property that we derived from Hermite polynomials, and Hermite polynomials are the eigenfunctions of harmonic oscillator problem. Now, when we have this anharmonic oscillator as the potential, we do not, or we cannot guarantee that this delta V equals plus minus 1 will hold. So, therefore, the beautiful relation that we determined or we derived based on harmonic potential of the harmonic oscillator problem, that is no longer going to be applicable here. So, therefore, delta V equals plus minus 1 or plus minus 2 and so on and so forth can happen, because now the potential energy is different, the potential operator is different. So, therefore, the Hamiltonian is different, the wave functions are going to be different, and the wave function, the beautiful properties of the harmonic oscillator wave functions that we used may not be applicable. So, therefore, within electric dipole approximation, where within the harmonic approximation of the electric dipole moment, we can still see anharmonic correction. That means, delta V equals plus minus 2 can also occur even when we truncate our dipole moment after the first order. And why is it happening? That can happen when we change the mechanical model of the system. That means, we are no longer working with harmonic oscillator potential, rather we have a more advanced or more complex harmonic potential to define the vibrational degree of freedom. So, therefore, even when we are electrically harmonic, we still can have mechanical anharmonicity. So, there are these two different sources of electrical anharmonicity. One is electrical, the other one is mechanical. The mechanical anharmonicity arises when we change the mechanical model from harmonic oscillator potential to an anharmonic potential, and electric anharmonicity arises when we do not truncate the electric dipole moment after first order, rather we consider higher order terms. So, this is the difference between the two different types of anharmonicities. Now, we will discuss one example anharmonic potential, and in this case we take a very popular potential, that is Morse potential. The blue curve over here is shown as the Morse potential, and the green curve here is the harmonic potential. So, harmonic potential is, that means V equals half k x square, and the Morse potential is shown over here, where there is a term d E 1 minus, and we have an exponential term over here. Now, before coming to Morse potential, let us look at the harmonic potential. We have the harmonic potential. The energy levels are shown as green lines. As you can see, the energy levels are equispaced. They are spaced by h bar omega energy difference. Now, when I look at the Morse potential, I have this d E term multiplied by this term. Let us look at some of the features of this Morse potential. We have one A term in the Morse potential, which is given by this expression k divided by 2 d E. I will talk about d E in a moment's time. This k is simply the force constant at equilibrium geometry. When you look at this equilibrium geometry, you see the harmonic oscillator potential and the Morse potential, they more or less agree to each other. They have rather similar curvature. So, therefore, this k of Morse potential is very similar, very close to the corresponding harmonic oscillator potential. Now, this A is given by the curvature at equilibrium k divided by 2 d E. Let us now look at this V form and then discuss d E. Suppose I go for r equals 0, that means the two atoms are extremely close to each other. When r becomes 0, in this term you would see that this r becomes 0. So, therefore, this term becomes e to the power a r or plus a r e. So, this is going to be an exponentially large term, and when I square this, it would give me a large quantity. When I multiply that by d E, which is a parameter for this Morse potential, this will give me a large value. So, that means at r equals 0, that means when the two atoms would try to come very close to each other, the Morse potential makes sure that the energy is not favorable. So, you can see it is a very high rise wall at smaller value of r. So, that is satisfied from Morse potential. Now, let us look at large separation of r. When r goes to infinite over here, so you would see that this term, this exponential term would become 0, because e to the power minus e to the power minus infinite. So, once that term becomes very small, so I am left with V as d E. So, the potential energy at very large value of r internuclear distance is given by d E. But what do we mean when I say that the potential energy at very large value of internuclear distance? That means at very large internuclear distances, the molecule actually would have dissociated. So, therefore, this d E is called the dissociation energy, or when at the potential energy, you can see the Morse potential in the blue curve at very large value of r, it attains a constant value, and this energy is d E, or the dissociation energy. Now, this dissociation energy is taken from the bottom of this potential, but we know that we know it from harmonic oscillator problem, the molecular vibration in the molecules have some 0 point energy. That means, V equals 0 energy level has certain energy by itself. So, when I want to break a bond, the energy that is required is not actually this d E, rather d E minus this 0 point energy, which is the energy at V equals 0, because when I dissociate a bond, the bond energy, if I calculate, I have to start from V equals 0 level and dissociate this bond. So, therefore, this D0 is called bond energy, and this is DE is the dissociation energy. Now, this is about the Morse potential. The other interesting thing that would come about is the energy of the Morse oscillator. So, in case of the harmonic oscillator, the energy expression was this term, the first term alone, h bar omega into V plus half, but in case of Morse oscillator, we see there are some correction terms. This is a negative term, and this depends on V, again V plus half square, note here, and then there are some terms which are specific to the particular system. For example, omega is the vibrational angular frequency, dE is the dissociation energy corresponding to that Morse oscillator. So, therefore, Morse oscillator energy levels are slightly different from the harmonic oscillator energy levels. One interesting thing that you would notice is that this correction term that Morse oscillator is providing depends on this V plus half square. So, that means when V is less, V is small, the correction term is also small. As V increases, the correction term becomes larger. Now, since the energy level, the correction energy is subtracted, so therefore, at larger values of V, this correction term will bring the higher energy levels closer to each other. For example, that you can notice here, the harmonic oscillator energy levels are shown in green line. So, they are equally spaced, but Morse oscillators are shown in blue lines. So, you see V equals 0 of harmonic and Morse oscillator, they almost overlap with each other. In V equals 1, you can already start to see the green line and blue line. That is because the Morse oscillator energy level has come down little bit. How much? V equals 1. So, therefore, 3 by 2 square of that. So, it has come down a little bit. For V equals 2, you can clearly distinguish for V equals 2, the energy has come down from harmonic oscillator compared to harmonic oscillator, and similarly for V equals 3, the energy of the Morse potential is lower than the energy of the harmonic oscillator potential. So, as you can see that the separation between two consecutive levels in the Morse oscillator are also decreasing. As you go higher and higher, you would see that the difference between two consecutive energy levels will become very small, and eventually this will become 0, and that limit becomes a dissociation limit. So, when the molecule dissociates, of course, you do not have that particular bond defined anymore. So, therefore, there is no discrete energy for that bond. So, then you are entering a continuum region. So, therefore, Morse oscillator beautifully allows the molecular vibration to become anharmonic. So, the inelastic nature of the molecule, the bond is beautifully described by Morse oscillator. So, therefore, Morse oscillator is widely used model for anharmonic potential. But Morse oscillator also has its limitations, although one plus point is that everything we can do analytically with Morse oscillator. But because of several limitations, we can also choose another different types of anharmonic oscillators, not necessarily this Morse oscillator alone. So, just to keep our discussion as general as possible, so we can define this EV now based on the information that we got from Morse oscillator. We can define now this EV, which is the vibrational energy level of an anharmonic oscillator, is the energy of the harmonic oscillator term minus some correction term. So, when I look at this, so one generally tries to express it in this particular fashion. So, where we have this chi e, which is called the anharmonicity. So, this is a coefficient that describes the degree of anharmonicity. So, this chi e would be useful for our future discussion. So, the point that I would like to remind you is that Morse oscillator is an example of anharmonic oscillator, but then you can imagine several other anharmonic oscillators as well. Now, we will discuss how we can do vibrational spectroscopy using this anharmonic oscillator. So, we are considering the general description of this anharmonic energy level. So, suppose now EV, so V can go from 0 to 0 onward. So, let us write down what is the energy of E0. You will see that the energy of E0 when V equals 0. So, this is simply half h bar omega minus V plus half is half. So, 1 by 4 h bar omega chi e, or all right. So, we keep it over there. Now, let us look at the E1. So, when V equals 1, I have the energy level as 3 by 3 half h bar omega minus. So, since V equals 1, so this becomes 3 by 2. So, 9 by 4 we can simplify them by considering h bar omega half minus 1 by 4 chi e, or simply h bar omega 3 half minus 9 by 4 chi e. E2, so when V equals 2, so this becomes 5 by 2, 20 by 5 4 h bar omega chi e. And so on. So, now these are the energy levels for an anharmonic oscillator. So, if I consider 0 to 1 transition, so E0 to E1, this transition will occur. To get that, I would have to subtract this number from this number. So, therefore, I am going to get E1 minus E0, which would come out to be. So, this is the fundamental transition. As opposed to h bar omega, we would see this transition at h bar omega multiplied by 1 minus 2 chi e. So, to get 0 to 2 transition, you would see that I would get E2 minus E0, that would come out to be So, suppose let us try to draw a spectrum. Suppose this is my h bar omega. So, I draw the grid in every h bar omega. So, suppose this is and so on, so on and so forth. So, now if I use harmonic approximation, I would have obtained the fundamental band at h bar omega, but within anharmonic correction, with anharmonic correction, I would not get h bar at h bar omega, rather I would get somewhere here. So, the difference that you see is because of this anharmonic correction. So, similarly, this 0 to 2 transition, so this is my fundamental transition. 0 to 2 transition under a harmonic approximation would have happened at 2 h bar omega, but here because of anharmonic correction of the energy levels, I am going to see here. So, this is 0 to 2, that is the first overturn. And 0 to 3 would be second overturn. So, of course, the intensity, as we already discussed, the intensity would depend on the magnitude of the second order or third order coefficient when we do the Taylor series expansion of the electric dipole moment. So, we see this fundamental band, first overtone, second overtone, and so on. There is one interesting feature is that suppose we want to consider 1 to 2 transition. If we try to find this, so E2 minus E1, this would come out to be h bar omega 1 minus 4 chi e. So, E2 to E1. So, what is E2 to E1? So, this is my I have over here. So, this is 0 to 1 the fundamental, 0 to 2 the first overtone. I am now considering 1 to 2. First of all, in the previous class we discussed that even though 1 to 2 transition is delta corresponds to delta V equals plus 1, but still its intensity is going to be low because not enough molecules exist at V equals 1 level. But now let us consider when under anharmonic approximation we see that the 1 to 2 transition occurs in a very important place. It occurs to the left of the fundamental band. So, the fundamental band occurs at h bar omega into 1 minus 2 chi e. The 1 to 2 transition occurs at further left. Of course, its intensity is going to be small compared to the fundamental band, but it is very easy to identify because this is the only line that would appear left or at lower energy compared to the fundamental band. All other transitions would appear at higher energy, the overtones or the higher harmonics, but there will be only one band which can appear at lower energy compared to the fundamental transition, and that band is known as hot band. And why do we call it hot band? For the simple reason that this line would appear only when the temperature is high enough for V equals 1 level to be populated. V of 1 to 2 transition is only will be only observed when there are enough number of molecules occupying V equals 1 level, and that happens when you have our temperature is high. So, suppose we want to prove whether this particular band is a hot band or not, we can simply record the spectrum again at a lower temperature or at a higher temperature, and at higher temperature you would see that the intensity of this band would keep on would increase. At lower temperature you would see the intensity of this band will decrease, but its position will not change because 1 to 2 transition energy would remain same. Simply increasing the temperature, we are simply populating V equals 1 level to more greater extent. So, therefore, more number of molecules would show V equals 1 to 2 transition. So, therefore, in today's class we would conclude here. Just before that, I would summarize that we discussed in today's class the vibrational spectroscopy of diatomic molecules, but we took our last class's discussion from harmonic to this class's discussion anharmonic. We saw that there can be two sources of anharmonicity in vibrational spectroscopy. One is electrical anharmonicity, which arises when we allow higher order term of the electric dipole moment to be present, and it can also be mechanical anharmonicity when we replace the harmonic oscillator potential with anharmonic oscillator potential. In this class, we discussed one particular anharmonic oscillator potential, that is the Morse oscillator potential. The advantage of using Morse potential is, of course, we can have analytical solution for that, but this Morse potential is merely an example anharmonic oscillator, and you can have different anharmonic oscillator that can perhaps represent your situation or system a little better. But in today's class, we understood how we can go beyond harmonic approximation in vibrational spectroscopy and what are the features what are the spectral features that we expect to see. Thank you for your attention.